I just want to start by introducing the example material and giving you an idea of what we're going to be doing today before we start to get into the files. So just to give you an expectation and so you know what to be looking for. So we're using example material that is a subset of a model for Columbia. We've reduced this to include just a small number of sources for demonstrative purposes. We tried to include various source typologies and a few different tectonic region types, but still made the model small enough to be run hopefully on everybody's computer and during a small amount of time here. So we want to provide the disclaimer, please don't use this model for any hazard applications. It's only for teaching purposes. And if you're interested in having the full model for this, you can visit the website of the SGC in Columbia, and the full model is available there. So just to give you an overview of the example, we're going to start out by running the engine, running through the engine, the PSHA example. And the reason for doing this is it will take a little bit more time on different computers. And so we want to make sure by the time we get to the part to review the results that everybody's job has completed running. And then while we're doing that, we'll go through an overview of the job files. And then we'll view the source model in QGIS and explore the hazard results there as well. What will this look like in QGIS? We're looking at a study area similar to what was used in the scenario examples, Antioquia, Columbia. And we're going to plot the seismic source model in QGIS. And the way that I created these shapefiles that we'll be looking at is using a command OQ normal to geopackage. And so this is a really useful OQ command for you to have in mind. It must be run through the terminal, and we won't do this today because sometimes there are some little bugs and differences in the version of OpenQuake that we're working on, but please be aware of this, this one going forward. We're going to look at 3 different source typologies, which all correspond to 3 different tectonic region types. And we're going to interactively look at the attribute table, which is a QGIS feature that's summarizing the different attributes of each of these shapes. And so when we do this, we'll have the chance to look for the different things we were specifying as we went through the seismic source model definition and the ground motion characterization definition. Then we're going to, for a set of sites that's covering Antioquia, we're going to compute the hazard. And we'll load the results into QGIS, so we'll have the opportunity to look at hazard maps. We'll also have the opportunity to look at hazard curves. And so someone asked earlier about the mean and the quantiles. And this is one of the ways that we can easily look at these. This plot of the hazard curves on the right includes the mean and 3 different quantiles, as well as the uniform hazard spectra. We can also plot these for individual or multiple sites. And so if there are no questions, we're just going to jump right into it and begin by running the example of classical PSHA. So I'll minimize my presentation here, and everyone please navigate to the material that you downloaded for this exercise. Can everyone see my screen okay? I know the font is not huge.
Yes.
Okay.
Maybe you can increase your font. And
yeah, I will once we're looking at individual files. I think it will be important. So please unzip the example material, and when you open up this folder, you will find module 3 example.qgz And this is the QGIS job that includes some of the materials. So let's open up QGIS. And it takes a moment for some of us. So while that's happening, please launch the Web UI for OpenQuake. So remember, Windows users, you have the icon on the desktop that you can click on. And for those of us on Mac and Linux, we have to come to the command prompt and we type OQ Web UI start. And so slowly this will open up. Oh, I already have this port in use because I opened it earlier. So I have to paste it here. And while we're waiting for that to load, everyone can click drive the OpenQuake engine. So remember, this is the triangle button here. I think I should load this in Chrome instead of in. That should be faster. Okay, mine's taking a little while to load, so I'll bring back up the slides to show how to start the job running. We're going to select play on the QGIS plugin. Then we're going to open up run a calculation, so select input data. And from the drop-down menu, instead of directory, we're going to select the zip file. And coming back to the material, we have job.zip, and this is the one that we're going to start loading. Since I'm having a problem with the port, I'm just going to pause for a second and try to fix it. While those of you, please start running your jobs, and I'll come back in a moment.
Indra, have you started the virtual environment for OpenQuake?
Yeah,
Okay.
it's just that 3.11 sometimes has some problems for me. Okay, here we go. So now I have the virtual environment running. So reconnect. Okay, so now we'll do this interactively here. So I selected drive the OpenQuake engine. You can see I've been running a lot of jobs lately, so you see this whole list here. We select run calculation. We see select input data, and we select zip archive. Okay. And then we're going to navigate. Here I navigated into my material for this job, and I select job.zip. Open. And so I can see it's just created, and now it says executing. And if I click on the console, I can see that it started to run. I come over here into the Web UI, and I can see also on the console that it started to run. So is everybody managing to run the OpenQuake job? If not, please you can either speak up or indicate in the chat. Okay, I see there were a couple of hiccups, but it looks like they were all resolved. Okay.
Yes, perhaps it's good to mention to everyone that because the job takes some time, please make sure if you have any error, write to us right now on the chat so we can see if you are having any error. For example, TREQ says the job failed. So if you can post in the channel the error message that you are getting, because if your OpenQuake is running okay, you shouldn't have any issue.
Yes, that's true. So we can scroll down to, I have an example where I failed and I have this error here, and it gives me value error for the reason that the job failed. And so this is what's really helpful for us to helping you to get the job running. Somebody ran out of memory. Okay. Unfortunately, there's not a lot we can do for this. But I think that, see, I don't know if we don't have any backup results in here, I guess.
It's the same memory error issue.
Okay, we have two memory errors. Okay, for those of you who ran out of memory, it would be helpful if you could tell us what kind of computer you're working on. And this might help us understand a little better the limitations of the demos we're using for these training courses. Well, I leave to Kata and to Shreyasvi to help those of you who are going through trying to resolve your errors. We'll start to go through the job files here. So navigating to, once we've unzipped the job.zip, and we navigate to the folder that's created called job, right away we'll see that we have 4 files. So we have a job in .ini. So this is familiar to you from the former trainings, but we'll use a few new parameters in here. Then we have 3 XML files. And so we have one defining the source model, one that's just the source model logic tree, and then we have the GMPE logic tree. So we'll go through each of these, and we're going to start with the source model. So I'll open up the source model. I'm going to open it in MacVim. I'll make it much bigger. But you can open this in any text editor. And the reason for that is because we use this NRML, natural risk markup language format, when we create most of the OpenQuake inputs. And so this is beneficial for us because it's human readable, so we can open it up and it's easy for us to go through the model and we can see the different tags that are telling us about the source model. So going through, we just have a little bit of header at the top, telling the computer about what language we're using. And then we start out by specifying the name of the source model. So this is just a description. It's a reduced model of Columbia, and it's giving us some information about what sources are included. So the first thing we see is that there's an area source. So we remember back to the area sources, what parameters do we need to specify for an area source? So we have the tectonic region type here. We've specified that this is in the active shallow crust. We've specified the geometry of the source. So this is just a list of coordinates specifying the area source perimeter. And this is similar to when we specify the geographic region. We need to specify in clockwise or in counterclockwise order the coordinates of the area source. And you'll see also that we have the first and last coordinates are the same. So we're closing the loop. So we also see some of the other familiar parameters. We have the upper seismogenic depth, the lower seismogenic depth. We have magnitude scaling relationships. In this case, we're using that Wells and Coppersmith that we saw in the theoretical component. We specify the rupture aspect ratio. Here we have the truncated Gutenberg-Richter MFD. So this is one of the instances that was brought up in the chat. So we have the A value, the B value, and the minimum and maximum magnitudes. In this case, for the truncated Gutenberg-Richter, the minimum magnitude is actually just specifying the minimum magnitude that will be considered by the OpenQuake engine. It's still a Gutenberg-Richter relationship that's extending back to m = 0. Then we specify a nodal plane and hypocentral depth distribution. So in this case, you'll notice we have multiple values that are assigned to these. And these are taking into account the aleatory variability. So the dip here, dip, rake, and strike are indicated for each of these lines, as well as a probability. So we're saying that in this area source, it's equally likely for for us to have an earthquake striking at 220 or at 170. We have a question in the chat. Minimum magnitude is the magnitude of completeness. No, in this case, the reason we're defining minimum magnitude equals 4 is because we have decided that's the smallest magnitude earthquake that's going to contribute to the shaking observed at the site. So if we used a smaller magnitude, we would be increasing the calculation without giving us more information about the shaking. So the hazard curve won't change. I'll answer the questions about creating this file after we finish going through the file. So we have the nodal plane distance, and then we have the hypocentral depth distance or distribution, sorry. And so again, this is indicating that we expect there to be earthquakes at about these 3 different depths, and that the most likely ones are the shallowest with hypocenters at 5 kilometers. And then as they get deeper, they become less likely. And so these two distributions have been assigned using focal mechanisms, using the depths that we observe in the catalog. And we've used those to decide which distribution values to assign. So carrying on through here, we have some more area sources, because we saw a few in the preview of the sources. So scrolling down, area source. So I'm going to navigate a little bit farther to the subduction. And so this is the first fault, called a complex fault source. And so we didn't actually see the complex faults in the case of in the theoretical component, but I'll explain them here. This is a source typology that's a little bit more specific geometry than the simple fault. And so rather than defining only the fault top edge, we're giving it a number of different edges that are defining the geometry. So these are just contours that are going through space, and we'll look at them in QGIS in a moment. So we're starting out defining the geometry of the subduction interface source. And still, we're going to have some of those other parameters. We have the interface parameter. We have, we've used a truncated Gutenberg-Richter MFD in this case, and we're specifying the rake, so the sense of motion occurring across these ruptures. But you see that we don't need, in this case, the nodal plane explaining the geometry, and we don't need to specify the depths. So then lastly, we have point sources. So these are sources that are representing some deep subduction seismicity. And the deep subduction seismicity in this case is in what's called the Bucaramanga nest, and this is thought to be a detached part of a subduction slab. So it's not quite connected to the subduction interface, but it's something where we see a lot of earthquakes happening, and so we need to characterize this this zone and include it in the seismic hazard model. So now that we see the point sources, each one has a point geometry that's specified by the position. So the latitude, longitude coordinates, the seismogenic depth, upper and lower, the magnitude scaling relationship, and the rupture aspect ratio. And then in this case, we're using an incremental MFD. And so part of the reason we've used incremental MFDs here is because this is a source in which the rates have been assigned using a smoothing that corresponds to the positions of seismicity. And so rather than assigning the A and B values, we've divided them up using this incremental MFD here. Although I think that this was a modeler decision by the modeler who created this. And so he chose to specify the rate at M5.5, the rate at M5.6, the rate at M5.7, and so on. In this case, we have just one nodal plane, one hypocentral depth, and we go on, and we see that we have more point sources because there are quite a few points representing the ruptures in this case. Okay, so this is a little bit of an introduction to the normal format for the seismic source model. And someone has asked, how do we create these? How do we actually make these source models? And so for this, I'll point you back to the hazard modelers toolkit and the model building toolkit. And we have those listed on this slide here. So we have a lot of information about that hazard modelers toolkit. And then from there, you can also get to, I'll post a link to the model building toolkit. The reason that we aren't creating these files in this training is because it's a little more advanced to be actually going through and creating an entire source model, and we found it more valuable to demonstrate the properties of the sources. Additionally, it's really recommended that you have some Python background in order to do this, and we can't guarantee that there will be an even level of that in the course. And so again, we just err on the side of demonstrating more components rather than creating them within the workshop. Okay, so Nima says HMTK document is completely outdated. It's true that it's outdated. However, the tools are still there, and the premise of the tools is still there. And so it's true that the document itself may not get you there, but this is where you can go to find the functions, and this is where and the HMTK functions are used within the model building toolkit as well. I will maybe ask Shreyasvi to post a link to the model building toolkit. Okay, moving on to the source model logic tree. So in this case, we're starting to see some of the terminology that we saw in the theoretical component. So we see logic tree branching level. This is actually this line is not needed in the newest versions of OpenQuake. But what we do see is specifying branch sets, each of which have an uncertainty type. This one is listing the source model. And in this case, we're using only a single source model. So so we see the name of the uncertainty model here, and the weight that's given to it. If you're interested in creating complex logic trees, we're directing you to the demos and the OpenQuake hazard demos. And there are a number of different examples in which you can apply the uncertainties there. Okay, third is the GMPE logic tree. And again, we see the NRML format. And so going through here, we see the apply to tectonic region type. So that comes back to the tectonic region type that's used inside of each of the source files. So these GMPEs will be applied to every source that has the tectonic region active shallow crest, and so on as we go down. We're specifying 2 GMPEs, so we specify them by their name with an uncertainty weight. And And doing the same for the subduction deep section, specifying a new branching level, a new set ID. And then so on for the subduction interface and the subduction interslab. Again, there are a lot of examples of these logic tree branches, logic tree XML files in the demos. And the most straightforward way is to create these is to follow the templates and to replace these lines here as is appropriate for your model that you're implementing. Okay, and
Sandra,
yeah.
before you continue, can I interrupt a second?
Yeah,
we have a question that asks, could I use a catalog with CSV format in OpenQuake? And before you reply, I would like to make a clarity for everyone. OpenQuake, the engine that we are running, is to run models, is not to develop models. So we need to divide two things. One is the modeling phase. For the modeling phase, you need earthquake catalogs, you need how to select the GMPs that are appropriate, how to build your source model, how to characterize your ground motion model, but that is not part of OpenQuake. OpenQuake only receives those files that you are seeing right now with Kendra and process them. So in the chat, you can find the link to the OpenQuake Models Building Toolkit, which is a toolkit that is used by the hazard team at GEM to create these files and to develop these models. Mm-hmm. You can use your own toolkits, you can use this toolkit, but to OpenQuake, you just provide these files when you are going to run a PSHA. It's independent of how you have produced them. You just have these files, OpenQuake reads them and run them.
Mm-hmm. Yeah, that's a very important clarification here. So yeah, unfortunately, in the case of developing a PSHA model, it's just it takes a lot more to create these job files than it does to create the files needed to run a scenario, for example. So we're not intending to build the model in this demo. We're looking at an example of what the files look like and then running the model through OpenQuake and visualizing the results.
Kendra, there is another question. Could I use catalog with .csv format in OpenQuake?
So again, the OpenQuake is not used to build the models, and so we're not introducing a catalog into OpenQuake. The OpenQuake toolkits, if you're going to use a catalog, the appendage can be CSV, but it's necessary to use the Hazard Modelers Toolkit format, the HMTK format, since this is the format expected by all of the functions in the model building toolkit, as well as the HMTK. And so that means the header fields must correspond to those labels. Okay. Moving forward to the job.ini file. So many of these fields should look familiar to you from the former work sessions of the workshop. So for example, the description here, again, we always recommend making a specific description so later you can find your job. We're specifying the calculation mode. And so in this case, we've specified classical. This is how we run classical PSHA. The random seed. This is also familiar from the former trainings, where it's indicating where the engine should start sampling from its random components. We have the geometry. So again, we specify the region, which is following the perimeter of the polygon, and then the spacing within that polygon. You can also provide a sites file, the list of sites, the same as you can do for the scenario analyses. Again, if you've forgotten how to do this, you can look at the examples in the demos or in the manual. The logic tree. So this is where we specify the number of logic tree samples. And when you type 0, this is taking the entire logic tree using every single end branch. If you've if you've created a very advanced PSHA model with an enormous logic tree, it may become impractical to run this in OpenQuake. And even for some of you who are having the memory error, this could be something that could help you in this case on a smaller machine. If you don't want to run every single branch of the logic tree, you can specify how many branches you want to run. However, keep in mind that your results will change. And so in the case of this job here for a small subset of Columbia, where we have only a handful of branches, we have just the branches coming from the ground motion logic tree, sampling will really change the results in this case. So next we have the ERF. This is the earthquake rupture forecast. And so this is where we're actually taking the seismic source model and generating the ruptures. So we specified all these parameters in the source model files that are indicating what the MFD looks like, how should the area and dimensions of the ruptures be determined, and so on. But what we need to specify in addition to this is how we're going to sample the magnitude frequency distribution. This can also be specified in the source files, but if you want to do it on a full model scale, you can write it in the job file. So this means that we'll take the MFD at every 0.2 units of magnitude. The rupture mesh spacing is indicating when we're computing the distance to the rupture, how big of squares on the rupture are we using to compute the measurements, because the engine has to find the distance between the site and the rupture. So it has to compute the distance at every single point along the rupture. Next, we have the area source discretization. So we've specified our polygon that delineates the area source, but we must turn this into a set of points inside the rupture, or inside the area at which points we're creating the ruptures. And then the complex fault mesh spacing is likewise the way that we're specifying the points along the rupture that are being used to, or along the source that are being used to create the rupture. So this also starts to impact the way that those ruptures are floated along, as we saw in the earlier component. So the next set is for the site parameters, and I won't go into much detail here because these correspond to the same ones that were used for the scenarios. We can specify the VS30 value as something to be used consistently across the entire region, or alternatively, it can be specified in that sites file. But since today we aren't using variable site conditions, we're computing for just a reference 760 meters per second VS30. These are some more advanced parameters used to specify more information about the site, and I won't go into detail on those today since they're computed according to the 760. So the next part is where we're pointing to our source model. And so this part's important because it's actually indicating the logic tree, not the source files, but the logic trees for both the source model and the ground motion logic tree. So this is where we're actually calling the seismic source model that we've implemented or are running. Next is the investigation time. And it's important to remember what you specify as the investigation time when you're interpreting your hazard results. Because if we remember back to how the expressions of PSHA manifest, the investigation time is what is used to convert between probability of exceedance and rate of exceedance. When we're looking at different return periods and whatnot, it's very important to know what investigation time we specified. So Next is where we specify the intensity measure types and levels. So here we've specified PGA as well as 6 different spectral periods. And here we're specifying the range of intensity measure levels for which we want to calculate the probability of exceedance for PGA. And so this is a new feature compared to how we've done the earthquake scenarios, because now we're creating entire hazard curves. So this is where we're specifying the values you will see on the x-axis of the hazard curve. And we can do this in a couple of ways that are shown here. The first one is to specify a list of values. And the next is to specify the minimum and maximum, as well as the number of levels, noting that the number of levels must remain consistent between each of the intensity measure types. And so here, the engine will compute on a log scale intensity measure values ranging from 0.005 up to 4. You'll notice that in this case, we've specified 3 different maximums depending on the intensity measure type. And this is because of which periods we expect to ultimately give the highest values. Okay, next is the truncation level. So we've set this to 3. We discussed this a lot in the scenario analyses. And in the case of PSHA, the truncation level is helping us to constrain the aleatory variability in the ground motion models. And so we're taking that Gaussian distribution about the median hazard prediction, and we're cutting it off at 3 sigma. In the case of PSHA, what this does is it just increases a little bit the hazard results by making for a given return period, because we're making it more likely that the higher ground motions will occur, but only a little bit. In the case of risk, I think you guys will talk about that more next week, and it's also been covered in the last 2 lectures as well. So the last part of the calculation is the maximum distance. And so in this case, we've specified a different distance for one of the tectonic region types, so subduction interface. We're going to compute the hazard from every source that's within 300 kilometers of the site. On the contrary, for the other tectonic region types, we're only going to consider sources within 200 kilometers. And we had additionally specified this default value. You can use a default just for the entire model, and specify only that default if you prefer to do this. This is another instance where the user has to do some sensitivity analyses and determine for themselves what the distance that they need to use is in their hazard calculation. And so we've specified 300 here for subduction interface because it's a fairly commonly used value, but many people argue it should be longer, and you need to investigate this for yourself. Finally, we're describing which outputs we want. And so in this case, we've specified, yes, we want to see the mean hazard curves. We also want to see these 3 quantiles for the hazard curves. You could specify as many quantiles as you please. We would also like to produce hazard maps. So we've set hazard maps equals true. We also want the uniform hazard spectra. So we said uniform hazard spectra equals true. And we also specified the probabilities of exceedance that we want to look at. And so those are the uniform probabilities of exceedance that will be generated for which uniform hazard spectra and hazard maps will be generated. And so I think we saw a question in the chat where someone asked, can you specify multiple investigation times in one job file? And no, you can't do that. But what you can do is use the investigation time with that conversion from probability to rate, and you can figure out which probabilities of exceedance you want to look at if you're interested in more than one investigation time. So the way that's specified is through POEs. Here we've specified 2% in 50 years, 5% in 50 years, 10%, 20, 50%. And so this is the way in which you would add that into the job file. And finally, we said, do we want the individual curves? So individual curves means, do we want all the realizations to be exported? And for this, we also said true. So are there any questions about the job files before we go into QGIS? Okay. I'm not seeing any. Okay. Oh, we have one in the chat. If spectral acceleration that we specify in job.ini is not defined in the GMPE, interpolation is done or the GMP is not used? Okay, good question. So yes, interpolation can be done, but the important part is that there is a spectral period both smaller and larger than the period of interest. So yes, we interpolate, but we don't extrapolate. Okay, and Nima saves his questions for the end. Okay, so we can see that my job completed running. I hope that I see some of you are still having trouble, but I hope most of you were able to complete the job. If we open the console here or in QGIS, we can see that mine ran in 677 seconds. We'd be interested to see how long it took for everyone else's jobs to run. We can also see, now note that what's printed out to the console changes a lot with every version of OpenQuake. So don't get too used to it in a specific form, but we usually get these details about what are the maximum map values, how big is my output, and just a lot of information about what was going on in the calculation. So moving back to QGIS, also in the console here, I can see that my job completed. And when we've opened this QGIS job, I have to right click on one of the layers and click zoom to layer. You may have to do that too. It's just a QGIS quirk. So starting out by just opening up this job, we can see some basic information about the input model that we just went over in the XML formats. And so turning off the source model for a moment just to orient. Here we are in Colombia, and zooming in, we have the area of interest, which is Antioquia, and the perimeters of this department, as well as all the other departments are drawn here. We can also see, I'll change the color here because it's a little bit dark. We can also see the faults that are mapped according to the SGC. And so we can think about these a little bit when we're looking at the source model and at the hazard results. So returning the source model to the viewer, we see that we have 3 different categories here. And we can use this identifier button to learn a little bit more about what we're seeing. So if I click on this one here, this is the complex fault source. And so I mentioned this when we were going through the XMLs, that complex faults are defined by a series of edges. So this is one of the more advanced versions of fault sources that we used. And so this is plotting the contours of the complex fault source. And so we can see by looking here, we see the ocean in the background here, the bathymetry, and we can see that this is a subduction interface source corresponding to that trench. And indeed, the name of this source is interface segment 6. And it's a little difficult in the viewer form here, but we can see a little bit of information about this source. So we can see the Gutenberg Richter, we can see which magnitude scaling relationship we're going to use, and so on. Secondly, we have the area sources here, and I'm going to view these in a different way. So I've selected the source model here. I made sure that it's highlighted, and I use the selector to select these sources and open up the attribute table. And so if I just want to select one to get the properties about it, I can select just a single one, bring that table back. And so I see here, okay, I'm looking at source ID 59. Every source has a unique ID. I can see that it's modeling active shallow crust. I can look at the magnitude frequency distribution and so on for this source. Someone's mentioned that the area sources look to be overlapped with the point sources. Yeah, this is true. In the real Earth structure, it's common that we see layers, different depth layers of sources that must be represented in different ways. And so here we have the active shallow crust, which is the shallowest part of the Earth, and that's represented by these blue polygons. And then the orange dots are representing the deeper seismicity that's representing, for example, here the Bucaramanga, the Bucaramanga deep seismic nest. And so it's often true that in map view, we will see multiple sources overlapping each other. I'd encourage you to look around at these to think about the source parameters a little bit. I think now we'll go ahead and load the hazard results and start to interpret them a little bit. So bringing back open the driver for the OpenQuake engine. I think this will be familiar to you all, but what we'll do is we'll find our job, example classical PSHA, Antioquia, Colombia, and we'll click on outputs. And we can check that we selected the right one because here, list of outputs for this calculation ID, and it's also written up here. And we can see that we have hazard curves, hazard maps, realizations, uniform hazard spectra. And so let's start out by loading the hazard maps. So here I'll click load layer. And I think we'll load, let's start out by just loading the 10% probability of exceedance for only PGA and only the mean. So we'll do this fairly simply to start. And we click OK. And when I close this window, I see, okay, my hazard map has loaded. So I'll kind of toggle off and on the sources. First, let's just turn them off. And we can see that there are some areas which have distinctly higher hazard. For example, closer to the coast, we seem to have higher hazard. Also, kind of coming over here by these faults, we seem to have some higher hazard. And so this may be indicating something about the sources, but it's important not to just jump to the conclusions looking at this. We have to continue to look at the disaggregation and so on. Not today, unfortunately, there isn't time. But we can also see, I turn off the layers here. We can see that some of these deeper sources are indeed contributing to the hazard here, and they must be impacting the higher results there. So the hazard maps, I think somebody's microphone's on. Could you please check? The hazard map plots the same way as the scenarios in that the QGIS plugin is automatically choosing which colors to plot and breaking down this range into some different layers. So then if we load a second map, so let's come back, back to the hazard maps. And this time let's add the 2% in 50 years. And so we know that this is a more rare instance of the ground motions we expect to see. So we can say, okay. And it's important to note that these are not scaled exactly the same. You can do that on your own by, for example, if you copy the style and do some QGIS tricks of your own to make them the same colors. But you can see automatically that, okay, now the hazard is higher for 2% in 50 years. And in these areas, these dark red areas, it's reaching 0.85 G, as opposed to at 10% in 50 years, it was only reaching 0.46 G. And so you can also see a little bit of change in the shape. And we won't interpret that in too much detail now. But these are some of the things we can do looking at the hazard maps. So now we'll go ahead and add the hazard curves. So in this case, I'm just going to load all the realizations, all the intensity measure types, and click OK. So again, that comes from the driver for the OpenQuake engine. Hazard curves, load layer, OK. And this one takes a little bit longer because it has to add more data for each of these sites. Okay. We have a question. If the IRMT cannot plot disaggregation results, then how do we plot it? You have to plot these on your own. The results can be plotted. They're just exported in XYZ data, and you can write simple scripts in Python or in MATLAB or GMT or any other plotting tool to create the maps yourself. So now that we're looking at the hazard curves, we need to open up the output type window over here. And so it's the one with the little squiggle on it, and it's going to be our data viewer to show us the hazard curves. And so you can automatically see that what it wants to show us is the PGA hazard curves for 4 of these quantiles. So let's zoom in and let's go back to placing our layers on. So we can see this was our area of interest in Antioquia, and I'll turn off the color just to make it easier to see. And so we can select, let's just select one of the sites. And so we do this using the yellow selector tool. It's you can have multiple different manifestations, and we select a site, and we can see that in the window here, we're plotting the mean, the quantile, the median, and another higher quantile. And so this gives us a little bit more information about the range of the results that we can see in this site. We can also use this to compare. For example, I will remove the quantiles, and I will add a site. So this is a kind of an area with moderate hazard, and I'll come over here and holding down Shift, select another site from the coast, and this site has higher hazard. So I can see that the hazard curve is higher here than it is in Antioquia. So so this is a way to interpret a little bit more too, not only which hazard or which site has higher hazard for one probability of exceedance, but they might be closer together for some other probabilities of exceedance. And in some instances, you may have sources that don't appear until later, and so the hazard curves may even cross. So the last data type is the uniform hazard spectrum. And so let's go ahead and load that last output type, I'm sorry. And so back to the driver, load layer, and we'll look at for now the probability of exceedance of 2% in 50 years. Select OK. And this works much like the hazard curves for the viewer. We can zoom back in again to our site in Antioquia, and we can select one site. Each of the gray X's is one site, and we can plot again the mean, the quantiles for this site. And so we can see it may be true that the mean is showing about 0.2 G for a spectral period of 1 second, but it's a little bit higher than that for the 85th quantile, and that can make a difference for some applications. Likewise, we can do the same comparison in which we compare site to site for different means and quantiles. And so I hope that this gives you a little bit of an overview of what these output types look like. The QGIS plugin is really useful as a first visualization from them, but remember that you can also output the results and use your own plotters and your own functions in order to make them look a little more like you want, or compare things exactly in the way you need to, as well as to share data and so on. And so one way to output those is to go into the web UI, and you can come here and you can download your hazard curves, your hazard maps, the uniform hazard spectra, the list of the realizations, all in the CSV format, which is a very straightforward format to use. And likewise, you can do that from the data viewer, or from the IRTM plugin, downloading these in this way.